to get you guys ready for your final and get you out the door done with your Math 21 requirement. All right, so let's take a look. We're at something new here. Chapter 9, all we got left is 3 sections, 9.1, 9.2, and 11.3. Probability distributions and expected value. So, what if a family is going to have 2 kids? They could have, 2 boys, a girl and a boy, 2 girls. What's the probability of that stuff? What's the probability, assuming it's half chance for boy, half chance for girl, which is very close. I think girls are slightly, if you go on Google or something, I think there's slightly more females born than males, just barely over 50%, I think, if I remember right. Anyway, real close to 50%. 50-50. So, what's the probability that you're going to have, 2 boys?
1/4.
How do you come up with that? That sounds good to me.
50-50 times 50-50.
Yeah, that's good thinking. Yeah, you could do it like a tree. You could say, whoops, get that clear. You could say, your first one's going to be a boy or a girl, and then your second child, after having a boy, you could have a second boy or a girl, and after having a girl, you could have a boy or a second girl. In other words, when all is said and done, you could have boy boy, boy girl, girl boy, or girl girl, and they're all equally likely, right? So, what's the chance you're going to have, 2 boys? Yes, like you said, it's 1/4. Each of these is a fourth, huh? What's the chance of 2 girls, a fourth? What's the chance of having 1 boy, 1 girl? Well,
oh no, I guess 1/2.
yeah, you could add those up, huh? And they'd be a fourth plus a fourth, 2/4, or a half. So the chance you're going to have 1 of each is a half. Chance you're going to have 2 boys is a fourth. The chance you're going to have 2 girls is a fourth. All right, so what's their question now? They're saying X is a random variable. And what is X? Where do they say that? Family has 2 children. Oh, number of boys. There it is. Number of boys. So when they talk about X, they're talking about number of boys. So I'm getting that from the words right here. Right? Number of boys. So what, and then down here, P stands for probability. So what's the probability of having 0 boys is what they're asking. They want me to put in this box, number of boys is 0. What's the probability of that? What's the probability if a family has 2 kids are going to have no boys, 0 boys? 1/4, because it's girl, huh? So it's just 1/4. They want a fraction, yes, so I just put 1/4. What's the probability they're going to have 1 boy?
Like just 1 boy?
Yeah, exactly. Yeah, it means exactly 1 boy. Because we'll get to the 2 boys in a minute. Yeah, good question. For clarification there, you're right. It's exactly 1 boy. Not 2, not 0. What's the chance you're going to have exactly 1 boy? Yeah, it's either one of these, so it's a half, huh? Really means 1 boy, 1 girl. So it's a half. And what's the chance of 2 boys? Well, that's a fourth. So those are the 3 answers. They're just wanting us to put those probabilities in there of no boys, 1 boy, and 2 boys. Does that make sense on that? Questions on that one? Let me flash that off, get that copy down. Okay, so 4 coins are tossed, and the number of heads is recorded. They want X greater than or equal to 2. See that right there? X greater than or equal to 2. Which of those 4 graphs has the shading on X greater than or equal to 2? Everybody see it's D? Because 2 and greater are shaded. That's all they want you to do. They're just simply saying, can you take this statement and figure out which shading it is? 2 or greater. We're going to get real with it in a second, get to what this stuff really means. But for now, just kind of laying out the theory. X greater than or equal to 2, shading 2 to the right. All right. Okay, so, yeah, before we do that question, having put that forward, let me come over here, let me make up a new game. I'm gonna make up a game. We're gonna do the, I'm gonna be a casino operator here. All right? And let's say if you roll a die, if you get the numbers, let me see. If you get 1, 2, 3, or 4, you win that amount. All right? You win that amount. If you get 5 or 6, you lose your bet. Let's say. You win that amount. So 1, 2, 3, or 4, you win that amount. So if you roll a 1, you win $1. If you roll a 2, you win $2. You roll a 3, you win $3. You roll a 4, you win $4. You roll 5 or 6, you lose your bet. Okay? The cost to play the game, meaning one roll, equals $1. So pay $1, roll the die. If you get a 1, 2, 3, or 4, you're going to win $1. You get your dollar back. Whenever you win, you get your original. So I'll put in here plus original dollar back, right? But if you roll 5 or 6, you're just going to lose your dollar. What do you think? Is that a good game to play? Is that a profitable game?
Yes.
Is that a game you should, if they offered that game at the casino, or one of your friends, you have a shady friend that goes, hey, I have this gambling game. Should you play the game?
Yeah.
Or not?
The odds are in your favor.
How do you know?
4 out of 6.
Yeah.
It's gonna net you at least $1 4 out of 6 times.
Yeah, that seems reasonable, doesn't it? Yeah, you can get at least $1 4 out of 6 times, huh? Yeah. Right, okay. And that seems reasonable to me too. What if the cost to play the game was $4? So you get your $4 back, so it's $4. They're saying, oh, okay, yeah, maybe that's too easy of a game. $4. You pay $4 and you roll the die one time. You get a 1, 2, 3, or 4. You get your $4 back, plus you win $1 or $2 or $3 or $4 on top of that. Or 5 or 6, you just lose your original 4. Lose your original $4.
It's the same.
Is it just as profitable?
Maybe higher risk, but it's better.
Yeah, it's riskier, but the odds are still in your favor.
Are they? How do you know?
Because 4 out of 6 times, you're gonna win at least $1.
4 6 times you win at least $1, right? Right.
4 out of 6 times you're losing $4.
4 out of 6, what's that?
4 out of 6 times I think you can at least win $4.
No.
Because don't you win your original 4 back?
Yeah, you didn't win it. It was your $4 to begin with. You didn't get it back. You only, but the casino pays you $1 or 2 or 3 or 4.
Oh, okay.
That's what you actually win, right? Net effect to your bank account, you went up by 1 because the original 4 was still yours. Your bank account went up 1 or 2 or 3 or 4, or it went down $4 if you rolled a 5 because you lost your $4 bet, or it went down $4 if you rolled 6. 5 or 6, you lose your $4. Your bank account is negatively affected $4. So, is that a good game? Is that a game you should play if they had it at the casino?
Based on odds, yeah.
Yeah, what odds? Just
The 2/3.
2/3 thing. Okay. What if they said it's $400 to play the game? It's $400. Roll the die.
Well, for only $1, $2, $3, $4, probably not, but,
Wait, no, what about your 2/3
well, yeah, I mean, the probability of winning is still good, it's just the return isn't.
Yeah, so it's not just the 2/3, is it?
Right.
There's more to it, that's what I wanted to say. There's
Right.
a couple of things going on. It's not just the 2/3, right? Yeah, you're still gonna win most of the time, but when you lose, you're gonna lose bad. So there comes a point where it's like, oh, no. If I'm gonna, 2/3 of the time I'll win some amount, but 2 out of 6 result, 5 or 6, I'm gonna lose $400? No, I'm not playing that game. You sense it, don't you? That's just too much. So it's both things are going on, aren't they? There's probabilities of winning and losing and how much you would win or lose. That affects whether something's a good game to play or not. Let's go back to the $4 thing. Is that good? Would that be? Let me. How about if they raised it a little bit? How about if they said $6? $6 to play the game. You can win 1, 2, 3, or 4, or you can lose your original 6 if you roll a 5 or 6. Well, let's get down to the science of figuring out exactly. This is the science that the casino industry lives and dies by. In fact, they live. They don't die. They do quite well, don't they? So here's the calculation that they know very well. It's called expected value, meaning it's a fancy average. So here's how it works. Here's how you decide whether something's a good game to play or not. This is how they know that every game they offer is in their favor, even though things are random. Here's what you do. It's just probability 1 times value 1 plus probability 2 times value 2 plus ... You just keep multiplying probabilities times value and adding them up. That's simply it. So in other words, let's talk about winning. That's a different word. Winning. So winning. Let's talk about the winning expected value. So you could win $1, right? What's the probability you're going to win $1?
1 in 6.
1 in 6. So 1 in 6 times 1. See how that's probability, 1/6, times value, $1. Plus, there's a 1/6 chance you'll win $2. Plus, there's a 1/6 chance you'll win $3. Plus, there's a 1/6 chance you'll win $4. Is that good so far? If we add those up, that's 1/6 plus 2/6 plus 3/6 plus 4/6. Add all those up, was that 5, 9, 10, 6? You can just use your calculator. It's 1.66666. I'll just round it to 1.67. You guys getting that in your calculator okay? Decimals are fine with me on the test.
You can convert it to math on that.
What's that?
You can convert it to fractions on the graphing calculator.
Yeah, totally. Totally convert it that way.
So the average you'd be winning is $1.
On average,
167.
you're going to win $1.67. That's what that means. That means on average playing this game, you will win $1.67.
And that's just your winnings, that doesn't take your costs into account.
Exactly. Yes. Is everybody okay with just the math calculation so far? So I just took probability times money, right? There's a 1/6 chance you win $1, so you roll 1. 1/6 chance you win $2, roll 2. 1/6 chance you win $3, roll 3. 1/6 chance you win $4, roll 4. And then you just hit the buttons, you calculate if you want. These whole numbers are over 1, so they go to the top. I just put the 2, the 3, and the 4 on the top. Because remember, whole numbers are over 1, they go to the top. Add them up, divide your calculator. You can just do the whole thing straight in your calculator, whatever. Round it off, 1.67. And what that means, that's money right there. That's the average winning, am I on the screen there? Yeah, per roll. So every time you roll the dice, on average, you're going to win $1.67, but we haven't figured in the cost yet. Every time you roll the dice, sometimes you'll win $4, sometimes you'll win $1, sometimes you'll win nothing. On average, you'll win $1.67. So, what price would you be willing to pay to play this game?
Less than $1.67.
Yeah, anything less than $1.67. Right. So if the casino said, like I originally said, hey, it's only $1 to play this game, yeah. If the cost was $1 per roll, on average, you'd be making 67 cents per roll. I mean, sometimes you'd win, sometimes you'd lose, but if you average after like 100 rolls, it would be very, very close to making 67 cents per roll if they charged $1.
So if I were to go to the casino with a notebook and just start doing math,
you know what you would find?
Yeah.
Here's what the casino has done this. They've done this very carefully. They have mathematicians that work it out. They would charge, say, like $2 for this game. Because now, if the charge is $2, you're going to make $1.67 per roll on average, but they're charging $2 to play the game, what's going to happen on average? So, yeah, the final, I'll just write it in right here. So, so we would take the final expected value would be the winning minus the cost, right? So you're winning $1.67 minus the $2 cost minus 0.33. In other words, you're expecting on average to lose 33 cents per roll when all is said and done, including the cost to play the game.
So even though you're winning more, you will ultimately be losing money.
Because of the cost to play the game. Yeah, because on average, you're really only winning $1.67 a roll. They're charging you $2.
Right.
So you're losing 33 cents. And you know what's funny is, I think it's interesting to me. Being a math person, I'm all about exact and precise, but probability is random. I mean, sometimes you win, sometimes you lose, sometimes the dice seem hot, or your hand seems hot, and sometimes it's cold, it's up and it's down. But you know what? They have something called, it's true to life, something called the law of large numbers, which means, do anything for a short period of time, and it might seem lucky or unlucky or whatever, but do it enough. Do it 100 times, 500 times, 1,000 times, 10,000 times, and the probability laws will start to show their force. It'll take over. Your lucky and unlucky and all that will balance out, and it'll be almost exactly what the probability predicts it will be over the long haul. You really will. It'll be like you're losing 33 cents. If you play this game 100 times, you'll be very close to losing $33, right? Multiply this by 100. 33 cents per roll. Roll it 100 times. Move the decimal 2 places. You can count on losing $33. It's almost exact. I wish we had time to do it here and roll 100 times and figure all the numbers out, but it would be so close. It always cracks me up when people say, I go to the casino, I just always win, and I just think, no, I know math better than that. I know. You might have a winning day, a winning weekend, you might have a winning month. But if it's your regular lifestyle and you roll the dice or play the cards or whatever thousands of times, the casino knows what will happen. They're not guessing. Every game in the casino, the expected value, of course, is negative because they're there to make money. So every game is in the favor of the house. And then what's funny is also they know exactly what they're going to make. They know how many dice are being rolled per hour. They know the odds and the averages. It's science for them. They know exactly what they're doing. So what that means is the wise, informed, math-wary person would say, hey, if I'm going to go to this casino, I'm just going to go in like I go to the movies or something. I'm going to pay some money, have some entertainment, and then I'm going to leave. It'll cost me, but if you speak that way to yourself, you're not gonna be taken. You just know you're gonna lose some money on average. You might have a lucky day or whatever, but on average you're gonna lose money, and maybe that's fun and you enjoy that, and then you're out of there. But if you go in thinking you're gonna win, that's when they've got you. Because they keep going, I feel lucky today. Today's my lucky day. I'm gonna do it.
Could they predict when people are gonna win as well? Like months that are gonna be spiked of jackpots or?
I don't know of some of how they program the machines and all that kind of stuff. So I just know about the things that are the cards and the dice that are not controlled by them. They can't program those kind of things. So I just know they know the expected value of every game in there, and so they know basically if 100 people play this every minute, they're going to be making $33 a minute. They just know how fast the money's going to be rolling in based on these expected value times how many per hour are playing in their casino. So it's just simply that for all those kind of games. Yeah. So does that make sense? So you can figure out anything probabilistically. I think it's really a neat calculation. You can figure out what's going to happen on average with anything that's random. But really the law of larger numbers take over. All right, so let's use that then to try these other questions now. All right, so here they're not even telling us what the game is. It's not really a very interesting question, but let's go ahead and crank it out. It's just practice. What's the expected value? So how do you do expected value? You just do probability 1. Oops, it's supposed to be a P there. Probability 1 times value 1 plus probability 2 times value 2 plus probability 3 times value 3 plus probability 4 times value 4. Just go right on through with the probabilities and the values. All right, so here we go. And so the probability is 0.2 times the value of 2. The probability is 0.3 times the value of 3. Probability is 0.2 for the next one times the value of 4. The probability is 0.3 times the value of 5. See how I came up with that? I'm just multiplying probability times value for each of those. Then just hit the buttons on your calculator. I don't know what all that is. I think it's like 0.04. No, it's just 0.4, huh? I'm getting confused. It's just 0.4, 0.9, 0.8, 1.5, 3.6? So the expected value, if that was some random game, expected value would be 3.6. That's good. So this is a way to find a probability average. That's what that is. Good on that? Questions on that? Okay, let's keep moving. All right, so expected. Whenever you see expected value, that's when you do the P1, V1, P2, V2, etc. Just probabilities times value. Now, where are the probabilities? We'll see P there is on the y-axis. See how the P is on the y? That means the heights are telling you the probability, and these must be the values down here. So in other words, this one's at, what is it? This one's at a 0.3, it looks like, 0.3 height. Whereas this one's at a 0.2 height. This one's at a 0.1 height. This one's at a, is it 0.15? And this one's at a, is it 0.25 height? Yeah, so just multiply the values, so that would be the 1 times the 0.3, the 2 times the 0.2, the 3 times the 0.1, the 4 times the 0.15, and the 5 times the 0.25. Everybody see how I did that? Just took the values times the probabilities. Oh, is that what it is? Yep. Good. All right, thank you. 2.85. That's the average value we can expect. That good? So expected value is simply just probability times value, just add them up. All right, roulette. Numbers 1 to 36 are evenly distributed between red and black. A player who bets $1 on black wins $1 and gets the $1 bet back if the ball comes out to rest on black. Otherwise, if the ball lands on red, 0 or double zero, the $1 bet is lost. One option is a roulette game. In a roulette game is to bet $20 on red. If the ball lands on red, you get to keep the $20 you paid to play the game, and you're awarded $21. If the ball lands elsewhere, you're awarded nothing, and the $20 that you bet is collected. What is the expected value of the game? So here we have an exact one. So you guys understand how the roulette thing goes, right? So 1 to 36 are red-black mix. And then there's 0 and double zero, which are green. on the roulette wheel. So that means really there's 18 red, 18 black. That's half of 36. 18, 18, and 2 green. The 0, 0, and the double 0. So there's 18 red numbers, 18 black numbers, and 2 green spots on the roulette wheel. Okay, so let's start by finding expected winning, and then we'll bring the cost into play. So what do you if you're rolling or if you're betting in your playing? What do they say? You bet. They're saying one option is to bet $20 on red. If it lands on red, you get to keep your 20 and are paid $21. So you win $21. What's the probability, right? You do the money. Remember expected value is value times probability. Or you can put, it doesn't matter what, or P times V, V times P, whatever. It's the value, the monetary value, times the chance of that thing happening. So what's the monetary? You could win $21. What's the probability? What is it?
9/19.
Is that what it is? It's 18 out of 38. Yeah, so it will reduce to be that, huh? Because there's 18 red. If you add this up, there's 38 total spots, huh? You add those up. All right, everybody seeing that? That's where he's getting the 38 on the bottom. He's right, which will reduce. Is everybody good with that? The probability of getting red is 18 out of 38. Out of 38 are red. So if you multiply that in your calculator, somebody got that? $9.95?
Yeah.
That good to there? Oh, wait a minute. Am I doing this one wrong?
Value for partner might be that $20.
What's that? Oh yeah, I'm not. I'm trying to make it as easy as I can, and I'm not doing it very clear for you. Let me. Oh, and that means that other one I did was actually backwards as well. Yeah, sorry guys, I'm trying to change the way I present this. I'm not doing it quite exactly right. Let me shift it a little bit. What you could do is you could just take expected winning is you've got to take the net result. The net result. So let me well yeah, but they do that other one the other way. Yeah, all right. So I'm trying to do it the way they do it, and they do it a little bit different. So here, let's do this. How much money do you actually get paid after you paid the fee for the game? You get your 21 back, and you get 21 and your original 20, so you get 41 back really. Is that making sense? So let's do it that way. Let's count getting our original 20 back as part of our winning. Yeah, to do it this way. So that'll come out, you'll have to do it like this. So that'll come out a little different. So it is, yeah, 1942, right. 1942. So that makes sense. So in other words, that's the average amount you're going to get back, right? After you've paid your $20. Everybody see that? See why I'm coming up with a 41? Because when you win, you don't just get back your original 20. You don't just get the 21 winning, you get your original 20 back. So you get 41 back. don't you? So it's 41 you get back times 18 out of 38, right? Because the probability of getting the red is 18 out of 38 times the $41 you paid back. So 1942 you would win back, but what's the cost of the game? So the expected value, the final expected value is the winning minus the cost. So it's the 1942 minus the $20 cost, and that's minus 58 cents, right? And so that's the real deal. That's actually true. Minus 58 cents. So if you're going to bet $20 on red, you can expect that you're basically going to lose about 58 cents per time you do that.
Do we put minus on the?
Yeah, let's go back and put the answer in. Minus here, I'll come back to it. So that makes sense. So let me go back then and correct that other game, as I did that wrong. I was forgetting to include the original bet as winnings. So you see how I got the 41, your original 20 back, and the 21 you won. So you made 41 bucks. You get 41 bucks back anyway, times 18 out of 38. And then you always have to take your winnings minus your cost, negative. They do want the negative, 0.58. So going back then real quick to this one, to this one, what was wrong about this game is I should have said, you don't just win $1, $2, $3, $4, right? You get your original whatever back. So if it was a $2 game, you'd get your original $2, so that'd be $3 back. Yeah, so this was wrong. This calculation was wrong. Yeah, let's forget. I don't want to try to patch it. This isn't going to work very well. Let's just go forward and we'll do it right from now on. All right. Okay, suppose you're invited to play a game in which you bet $1 on any number from 000 to 299. If your number comes up, you get 225 bucks. Find the expected winnings. All right. Find the expected winnings. Expected winnings, that I don't know why they're saying it that way, just expected value, whatever you want to call it. They want the final expected thing. So here we go. So I call it winning, or let's just call it income. I don't know what else to call it. You know, there's what you're going to collect. Okay, so what are you going to collect? Well, you're going to win. You're going to win $225, right? That's the value times the probability. What's the chance you're going to win $225? 1 out of 300. There's 300 numbers in 0 to, right? Because we include 0, right? 1 to 299 would be 299. Then there's 0. 0, 0, 0, 0. So there's 300 numbers there. So the income, if you multiply that together, is 0.75. That's the money coming in. That's what you can expect to take in per bet. So the final expected value or winning, let's call it expected, is income. Maybe I should call it income minus cost. Whatever you want to call that. It's money coming in minus money going out, basically, right? In minus out. Yeah, we could do it that way. We could say in minus out, you know? So what's the income? Well, 0.75. What are you paying out? $1. So what's the expected? You're losing 25 cents. That good? Everybody see how we're doing that? Losing 25 cents on average. No questions? We good? All right, so everybody says you just take the value times the probability, get that number, and subtract the cost of the game. So, a contestant at a fast food restaurant offered the following cash prizes and probabilities of winning on one visit when a customer buys an order of French fries for $1.71. Find the expected winnings if the player buys 26 orders of French fries in multiple visits. Let me see, is there, okay. So yeah, we'll just do the whole final answer here. All right. Can we figure this out? So you know how to do income, first off, right? It's just probability 1 times value 1 plus probability 2 times value 2, etc. So the income will be this money times that probability, right? $100,000. What's the chance? 1 over 8,504,860 plus 50,000 times 1 over 302,500. Good so far? Plus 10,000 times 1 over 282,735. Is that on the screen? Yeah. Plus 1,000 times 1 over 153. $153,560 plus 100 times 1 over 104,560 plus 25, 1 over 9,540. Wow, it's tedious. So you got to do all of that for the income calculation. And then when you're all done, you got to subtract out the cost of an order of fries. All right, so I'm going to do that with you. See what we get.
When you get the answers to each one, can you round each one, or you have to?
No, you better keep them going. You better not round each one. Yeah, keep it rolling on your calculator. Just type it all in like that.
21,774 point.
That sounds kind of big. Calculators never lie?
No.
Okay, I'm getting 0.2225050938. Did you guys get that? I'm not done yet. That's all of this. I just put those guys in the denominator. Does that make sense? I just did 100,000 over this one plus 50,000 over, right? Because the whole numbers just go to the top, don't they? Right? These are just fractions. Plus 10,000 over 28275. Just add them all up. I got the 0.2225050938. Now, that's the expected amount we would receive. 22 cents, basically, right? 22 cents. Don't round it yet, though. Careful. Never round till the end. I'm going to leave all those digits till the end. Now, what's the cost of the fries? $1.71. So always take income minus the cost, right? So that's the 0.2225050938 minus the $1.71 cost. keep it rolling on your calculator screen, and I get negative 1.48749 In other words, negative $1.48, or 49 maybe it would round to, right? And they said that's per order though. That's per order of French fry. You tracking with me? Per order. How many orders? 26 orders. So now times 26, keep it all on your calculator screen, minus $38.67. Let me double it. 38.67. This is the right. So I just kept it all on my screen. I never rounded till the very end on that. Does that make sense? Everybody see how I did that one? That was a really messy one. So I took the different prizes times the probability, times the probability, times the probability, which really meant over. The probability was the bottom. So I just took 100,000 over, plus 50,000 over, plus 10,000 over. Okay, I've added them up in my calculator. Got this 0.2225, big old number. Subtracted the cost, right? We would take income minus cost. Got that negative and then multiplied, because that was per order. That was every time you order fries, 26 orders, so times 26. So what does that number mean? What does that 38.67 mean? Do you understand what that means? That means if you place 26 orders of French fries, you can expect to lose $38.67. On average, that'll be your total loss. You'll get the fries, and you might get a prize here or there, but when all is said and done, that's what you can expect to lose. For those 26 orders. So is it making sense how to do that calculation? Just tedious, huh? That was terribly tedious. Terribly tedious. Yeah, I'm going to leave that. You try it later with your calculator. If you have trouble, come grab me. Be glad to help. But I want to make sure the main concept is clear, right? Just multiply probability times value, get your answer, subtract the cost. And then if you're doing multiple orders, times the number of orders. I did times 26 orders. There we go. All right. So they're saying, hey, is that valid or not? Is that probability distribution valid or not? What do you think? How do we know if it's valid or not? Say anything about it? What if I told you guys, what if I saw the weather report on the news tonight and it said 30% chance of rain tomorrow, 80% chance that it's not going to rain? It'd be time to get a new weatherman because that one's broken. Right. That weatherman might not have his job the next day because that's impossible. It's got to add it to 100%, right? So, do you see what we're looking at here? These are the probabilities, right? The P. They have to add it to 100%. If you add them up, I can already tell, look, we've got 4 quarters right here. 4 quarters is $1. That's already 100% right there. And then 10% more, they're going to add it to 1.10. That's the same as 110% in a decimal. I mean, 110 percentage is 1.10 decimal. And it's not allowable, right? The decimals have to add up to 1.0, which is the same as 100%. They can't be more. So that's not valid, right? The random variable does not sum to 100. Oh, no, I'm sorry, that's not it. The probabilities do not sum to 1. That's what we're talking about. Here's our answer. It's invalid because the probabilities do not add up to 1. They've got to add up to 1. You can't have this rain, no rain craziness. It's just not possible. Is that good? Everybody see that? So how do we find, call this one X. he's missing there. How do we find that x?
Subtract all the probabilities from 1.
Yeah, subtract all the other probabilities from 1, because they have to add up to 1, huh? So I'm just going to add them all up and then subtract from 1. So add them all up, 0.01, 0.21, 0.19, 0.43, 0.03, what do those have to be? 40, 83, 86, 87? 87, and then 1 minus 87 is 13. That's got to be x. The missing one's got to be 0.13. Is that good? Questions on that one? Right, so again, the idea is the probabilities have to add up to 1.0, don't they? 100 percentage or 1.0 decimal. All right, let's keep moving. Okay, so there we have a used car dealer gets complaints about his cars as shown in the table. What's the average number of complaints per day? That's what we're trying to figure out, right? That's what expected value is like an average, huh? So if he gets 0 complaints 2% of the time, he gets 1 complaint 7% of the time, 1 complaint in a day. He gets 2 complaints in a day 18% of the time. 3 complaints in a day, that's 20%, huh? 4 complaints in a day 33% of the time. 5 complaints in a day 14% of the time. 6 complaints in a single day 6% of the time. Those are the rough days. 6 complaints in a single day, and that happens 6% of the time. So what's the average number or expected number of complaints per day? How do we feel? So how do we do expected? Value times probability. Value times probability, etc. Just keep adding up value times probability. So 0 times 0.02, 1 times 0.07, plus 2 times 0.18, plus 3 times 0.2, plus 4 times 0.33, plus 5 times 0.14, plus 6 times 0.06. And that's all there is to it. There's no cost in this one, is there? It isn't like we have to subtract the cost. Right? When there's a cost to play the game, that's at the end. So first one to a number, somebody got it?
3.41.
2.41?
3.41.
What's that?
3.41.
3.41. Anybody else getting that? There we go. So on average, he expects about 3.5 complaints a day. That's what that means. Is that good? Questions on that? All right, 7P3. 7P3. Well, do y'all have your calculator with you? I'll show you how just to do it on your calculator. So if you have a TI, some kind of TI, it's under the math, hit the math button over on the left side. Hit math, and then go across 3 times to the PRB menu, and then go down, and you'll see NPR. That's what you want to use. Actually, I messed up. We should have put the 7 in before we started this. So actually, first you got to do the 7. So let me put it here. So first you got to do the 7. Then you got to do the math button and go over and choose NPR, and then you got to hit the 3 and then enter. That makes sense. Do the 3 first, do the math NPR thing, do the 3 last, and then the enter.
210?
I believe that's right.
What is that actually doing?
Yeah, I'll explain the real life significance in a second. But let's first off make sure we can crank it. You guys able to get that in your calculator? So hit math and go over to the PRB 3 times over, the probability functions. This is a probability kind of thing. So first the 7, then the P, and then the 3. 7P3, hit enter, 210. About right? Yeah, it is 210, yeah. Good? 210? Y'all able to get that? grab me after if you're having trouble doing that. Yeah, what that means is if you have 7 objects, how many ways are there to pick 3 and put them in order? So in other words, if you have 7 books in a box and you're going to pick 3 to put on your shelf in a certain order, there's 210 different ways to do that. It's amazing. Out of 7 objects, pick 3. If there's 7 people, there's 7 of us in the room. There's 7 of us in here. So 7 total. If somebody entered the room all of a sudden and was going to pick 3 people, the first one was going to get $20, the next one was going to get 10, the third was going to get 5. They just picked 3 of us at random. There'd be 210 different ways to pick 3 of us in a certain order. That's what that means. 7, pick 3, where order matters. Let's do that one. So 8C3. Use your calculator again. Is it 56? Able to get that?
Way easier than the first one.
Yeah.
What's that?
It is way easier than the first one.
The 9.1?
Yeah.
Yes, right. It'll get more tricky. They're leading us into word problems. These are the tools we'll need to do the word problems. Never stays easy for long, huh?
Yeah.
Always starts easy. Yeah, so everybody good there? That's out of 8 objects, choose 3, but order doesn't matter. That's the difference between the P and the C. They're both out of whatever, pick whatever, or choose whatever, but it's whether the order matters or the order doesn't matter. I'll talk more about that as we go. So, you able to get that? Having trouble grabbing? Okay. Now, what does that mean with that exclamation point to the right?
Between 6, 5, 4, 3, 2, 1 after that.
Yeah,
Something along that. Or
It
it'd be
mean-
8. Yeah, it'd be 8.
all the way down. Yeah, it doesn't mean like 8. You're like really excited about it. It means start at 8. Whoops, that wasn't an 8. That means start at 8 and go all the way down to 1. Yeah, exactly. It's called factorial, and it's also on that same math probability menu. Did you see it there? You can just use your calculator. Some really big number. Here, I'll do it too. 40,320. It's called 8 factorial. 8 multiplied all the way down to 1, 40,320. Again, that's useful for probability, real life situations. We'll see it in a minute. All good with that? Finding the buttons, able to crank them out? Word problems starting at 10. Okay. The owner of a stereo store wants to advertise that he has many different sound systems in stock. The store carries 8 CD players, 7 receivers, and 9 speakers. Assuming a sound system consists of one of each, how many different sound systems can he advertise? Does that make sense? Let me put it to you this way. What if I have 3 pair of pants I can wear and 4 shirts? Let's say 5. 5 shirts. If I have 3 different pair of pants and 5 different shirts in my closet, how many different outfits can that produce?
15.
Yeah, you just multiply them, huh? Does that make sense? Because I could wear pants number 1 or pants number 2 or pants number 3. And each of those can go with shirt 1, shirt 2, shirt 3, shirt 4, shirt 5. Shirt 1, right? Can go with shirt 1, shirt 2, shirt 3, shirt 4, shirt 5. Shirt 1, shirt 2, shirt 3, shirt 4, shirt 5. You can see in the end there's 15 different outfits. So you just multiply the numbers together, don't you? 15 outfits. Look at that. 2 weeks. I won't wear the same outfit for 2 weeks. Just 3 pants and 5 shirts. 15 outfits. I try to reason with my wife this way about her closet, about how many outfits are really needed. And she's got a math degree, but somehow it just doesn't come across. All right, so the shoes have to match the, All right. So let's get back to the CD problem. How many different sound systems? So a sound system has a CD player, a receiver, and a speaker. So how many different combos of all those are there? What are we going to do with those numbers? Just multiply them, yeah. Because there's 8 different CDs, 7 different receivers, 9 different, so different combos. So whenever you put things together, like shirts and pants, or speakers, CDs, and receivers, you just multiply them together to get all the different combinations. That's what this section, by the way, is all about. It's like how many ways are there to do different things? And so we're figuring out how many ways to set up the sound system. So that's some big number, which I don't know. 504? Okay, thank you. A lot of different ways to set up the sound system. So you just multiply them together. Isn't that good? Like different ways of, how many different ways of doing things? Well, because it helps. Like, for example, what if you're a business, okay? And you're setting up and you're going to say, okay, in our building, we're going to have 5, our gigantic downtown building, 5-digit phone extensions. How many wants to have 5-digit phone extensions with the first digit not being 0? How many different extensions are possible? You want to have enough to cover all your employees. So how many would that be? Like if you're going to, everybody gets a 5-digit extension, the first digit can't be 0. How many different extensions are possible?
Multiply by 4.
Well, let's do it like we did the pants and the shirt, or the, what was it, the sound system, right? Let me put it to you this way. Options, wait, no. Number of choices, or decisions, I'm sorry, I forget the way I say it. I teach this every semester. Number of decisions, and then options for each decision. I think that's a real clear way to solve these problems. So let's think about it this way. What if you were going to pick for yourself one of these extensions? My extension is going to be 37092. I'm extension 37092. It's a 5-digit extension. I just picked it at random, right? So notice it really helps. These questions can be kind of tricky. It helps just to do one sometimes. So there we go. 3709. I just picked an extension. Now what I really want to do is find out how many total extensions are possible. Having picked one, go back and ask yourself, okay, how many decisions did I just make? And how many options were there for each decision? So we'll wrap up with this problem. Let's just think this one careful and we'll stop there. When I picked 37092, how many decisions did I make? Well, 5. I picked a 3, picked a 7, picked a 0, picked a 9, picked a 2. I made 5 decisions. So for each of those decisions, put a line. 5 decisions. Okay? Just like when I got dressed this morning, I picked a pair of pants and I picked a shirt. You know, I might have had 3 pair of pants and 5 shirts times together, 15. Then once we get these numbers, we're just going to multiply them together. 15 different outfits. Right? I made 2 decisions this morning. Pants and shirt. 3 options for the pants, 5 options for the shirt, multiplied together, 15 different ways I could have got dressed, right? So that's what we're going to do with picking an extension in a lot of these problems. Decisions, options. So when I picked 37092, I made 5 decisions. For the first decision, for decision number 1, how many options? Yeah, only 9, because I couldn't pick 0. Remember? The first is not 0. So I could pick 1 through 9. I could not put 0 in the first spot, they said. I had to pick 1, 2, 3, 4, 5, 6, 7, 8, or 9. 1 through 9. I had 9 options, didn't I? How about for my second? These are going to be multiplied. How many options for decision number 2? 10. I could have picked 0 or 1 through 9. How many options for decision 3? 10. And on we go. 10, 10, right? Decision number 4, decision number 5. Is that making sense? Multiply those together. 100,000, 1,000, is it 90,000? Total. There's 90,000 different total extensions that are possible. 90,000. That'll cover 90,000 employees. This is the kind of thing they do when they figure out zip codes, license plates, things like that need to cover a big crowd. They make sure the options are going to cover the population they're intended to cover.
So there's no shortcut to that, that's when you have to
Yeah,
grade it out?
yeah. Decisions options, yeah, you do. Especially because they made one of them special, like,
Yeah.
that's why. If they didn't do that, you could just have 10 to 5th power.
Right.
Yeah, right. That makes sense? We'll do more about that next time. That's not due yet. The other one's due. 9.1 we did finish. So 9.1 will be due Thursday. We'll do 9.2 later. We'll finish it later. So we'll stop there.